Number 13, a plane is flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour. And it passes directly over a radar station. So I have a plane flying overhead. There's my plane. It is exactly 1 mile high. And it's traveling at a speed of 500 miles per hour. I'm going to put it going in that direction. All right. We have a radar station on the ground. Here's my little radar station. And it says, find the rate at which the distance from the plane to the station is increasing when it's 2 miles away from the station. Okay, so my picture is a little messed up because if I do this, it's coming towards the radar, and so the distance between them is decreasing. So what I'm going to do is I'm going to change it around a little bit. I'm going to put the radar station like this over here. There's my radar station. And the plane's traveling 500 miles per hour that way, and let's just keep in mind that it's 1 mile high. Now, what we're interested in is knowing, find the rate at which the distance from the plane to the station is increasing when it's 2 miles away. So the distance between the plane and the radar station is going to be this distance right here. And this is my general picture. Okay, this is my general picture. General. And so this red line is growing as this plane goes away. What I know for sure is that this stays 1 mile high. So I could label this like a right triangle here. I can label this 1 mile. And this is changing. I don't know, I need to see how fast it's changing, so I need to label it. Since it changes throughout the problem, label that Z. All right, now the specific instant in time that they're talking about, we have the radar, we have the plane, and we have our triangle here. And we know this is 1, and that we know that we're interested in when it's 2 miles from the radar station. So when Z is 2 miles, that's our instant in time. And what we're given is really the only rate that we're given is this 500 miles per hour. So we need to somehow relate that to the plane. So this point right here is moving in this direction, okay, at 500 miles per hour. And what we can do is we can imagine that that point corresponds to this point. And so as that plane moves, this point moves, right? These 2 points move this direction at the same rate. And so let's label the distance from here to here. Let's just call this x. And that means the plane moving at 500 miles per hour means that x changes dx dt at 500 miles per hour. We could say mph, but I'm just going to do it that way. That's what we're given. What we want is to know how fast the z is changing with respect to time at exactly the moment that z is 2. One of the common mistakes students make on this problem is that when the word problem says the distance between the plane and the radar station is 2, they'll say this distance is 2, but it's actually the straight line distance from the radar to the plane. All right, so we just need to come up with an equation that somehow connects this variable x to the variable z. We go back to our general picture, and you can see the Pythagorean identity on the triangle. We know that x squared plus 1 squared must equal z squared, which means x squared plus 1 equals z squared. This is my equation, and now I'm going to differentiate it with respect to time. So I take the derivative of x squared with respect to time, and I'll have 2x times dx dt plus the derivative of 1, which is 0. That must equal 2z, and then again chain rule dz dt. And I can divide both sides by 2 right away. And so now I can fix everything in time. Do I know x at the moment in time? Well, do I know what x is? Not yet. I can actually figure out what x is, though. I'm going to be able to do that because I know this side and this side. Do I know dx dt? Yes, it's 500. Do I know z at the moment in time? Yes, z is 2. And do I know dz dt? No, but that's what I'm trying to solve for. So the only thing I'm missing here is x. So let me go back over here. X squared plus 1 squared, which is 1, must equal 2 squared, which is 4. So x squared must equal 3. So x is positive or negative root 3. But because it's the length of a side of a triangle, I'm going to say root 3. So now I'm just plug everything back in. X is root 3. Dx dt is 500. Must equal z, which is 2, times dz dt. And then I'll divide both sides by 2. That'll become a 250. So I'll write it this way. 250 root 3 is equal to dz dt. And do we want to get this as a decimal? Let's see what the book does. Yeah, they get an approximation. Now, I'll do the approximation, the decimal approximation, but what is z measured in? Well, z is a distance, right? Z is the distance from here to here, and we're measuring everything in miles. So this is going to be miles over time. Time is measured here in hours, right? So this should be miles per hour. So if you approximate that, or get on your calculator, it's 400, about, dz dt is about 433 miles per hour. That's how fast the distance between them is increasing. So if I had a rope here connected to that plane, at exactly the instant it's 2 miles away from me, that rope would be coming out of my hand at a speed of 433 miles per hour. That's rope burn right there. That would not feel good. All right. Number 14. A street light mounted on a pole. It's 15 feet. Light's coming out in every direction, right, from that light. A 6-foot man walks away from the pole. So here's a 6-foot man. He's running, walking, however, he's moving away from the pole. He's moving away from the pole at a speed of 5 feet per second. And remember, he's 6 foot tall. 6 feet tall. How fast is the tip of his shadow moving when he's 40 feet from the pole? So let me draw the general picture. I'm going to draw this with triangles. So as the light comes down here, hits him, it creates his shadow on the ground. Here's his little shadow. Oh, he's missing an arm. Here's his shadow on the ground of him running. So the light is coming down here like that. So our general picture looks like this. We have a 15-foot side of a triangle coming down. We have a 6-foot side here, right? And this point is moving this way, right? That's all we have in the problem. We can say, since this point is moving that way, let's call the distance from here to here x. And so that this point is moving with the speed dx dt of 5 feet per second. Now the instant in time that we're talking about, we have the same picture. here's 6, here's 15, but the distance here to here is 40. So now it's fixed, all right? What we're given in the problem is the speed at which he's moving, which is the speed at which x is changing. So we have that we're given dx dt is 5 feet per second. I'll just put s. We want to know how fast the tip of his shadow is moving. So the tip of the shadow is right here, and it moves down this direction as he moves. Important thing though is we want to know what its speed is relative to a fixed object, to the pole, right? Because if I say how fast is this point moving away from him, well, he's moving also, so that's a different question. We want to know how fast this point's moving. So if we have the fixed pole, if you're just focusing on that point, how fast is it moving? So let's call that point S for shadow. And so what we want to know is what ds dt is. And we want to know that at the moment that x is 40 feet. These are all feet, right? 15 feet, 6 foot, 40 foot. And that's it. So we just need to find a relationship now between two variables, x and s. And we go to our general picture, and I hope that you see in our general picture that we have two triangles, right? So I'm going to come up here. I'm going to draw first this outer triangle, right? This outer triangle would look like this. It would be 15 and then s. And then we have this smaller triangle right here, which would be 6 here. And then the distance from here to here is this distance take away x. So this will be s minus x. Just think about it. If s was, let's say, 40, and let's say x was 10, then this distance would be 30 because you're doing 40 minus 10. So s minus x. Now these are similar triangles because they're both right triangles, and they both have this angle in common, which means that this angle is the same as this angle. So since they're similar triangles, I can set up a ratio of the sides. And the ratio can be set up however I want. I could do this over this must equal this over this. I could also say this over this is equal to this over this. It's really up to me. I'm going to do it this way. I'm going to go s over 15 is equal to s minus x over 6. And that is because I want to keep my variables on top. So I'm going to say s over 15 must equal s minus x over 6. So what I've done is I've created an equation, which is what we needed, right? We need an equation that relates those two variables together, and here it is, an equation with s and x. And now I can differentiate that. Now before I differentiate it though, I'm going to clean it up. This is 1/15 s equals 1/6 times s minus x, like that. And then I can just differentiate with respect to time. So 15 times s, derivative of this, 1/15 s is 1/15, derivative of s is ds dt, equals 1/6 comes along for the ride, derivative of s is ds dt, minus derivative of x, which is dx dt, and that's it. So do we know any of these things? Well, dx dt we know is 5, so that we've got, and that's the only thing in the problem. There's no x's or s's, right? So that's kind of weird. I actually don't even need this 40 feet. In order to determine how fast the shadow moves with respect to time, it looks like in the equation it does not matter at all what x is, which means that shadow is always moving at the same speed all the time. That's weird. That seems weird, at least for most people that seems awkward. But let me plug things in. I've got 1/15 equals 1/15 ds dt equals 1/6 ds dt, and then minus, that was 5, so I'll say minus 5, like that. And then I'll distribute, so 1/15 ds dt equals 1/6 ds dt minus 5/6. And then I'll go ahead and, let me do this. I'm going to move this to this side so it's positive. I'll move this to this side. So I'll have 5/6 equals, now I'm going to take 1/6 ds dt. I'm going to subtract from it 1/15 ds dt. So you have to do some fraction stuff here. What's 1/6 minus 1/15? So it's 15 minus 6 over 60, 80. So 9 over 80. 3 doesn't go in there. 9, 80, is that right? 9 over 80 ds dt. And then to get ds dt by itself, I multiply by the reciprocal on both sides. So I'm doing 80 over 9 times 5 over 6 equals ds dt. And I know that cleans up. 2 goes into there 3 times, and 2 goes into there 40 times. So 45, 90 over, wait, why did I say 90? My goodness. 200 over 27 equals ds dt. Something doesn't look right here, but let's see here. What number was this? $20, 200. I'm sorry, it's Monday. It feels like a real big Monday here. 3 goes in there, 18. I cannot do simple arithmetic right now. Hold on. No, something ain't right. Hold on, something ain't right. 5 over 6, that's all right. 1/6, 1/6, 1/6, 5/6. Brought that to the other side. 1/6. So when we did 1/6, 15 minus 6, 9 over 6, 60 plus 30. Oh, 60 plus 30 is 90. My goodness. Okay. There it is. 90, 90. My bad. And that's going to be 1/10. Okay, that's a little better. So that means, let me fix this here. Erase this. Oh, you're fine. This is 1/10. And then I multiply both sides, and I get 50. Multiply both sides by 10, I get 50 over 6 is ds dt. And then reduce this, 2 goes into each of those, so 25 over 3 is ds dt. Okay, so I did that wrong. All right, so there's our answer. Now, what is the units? S is the measurement from here to here, and that's a length, and everything was measured in feet, so that's going to be feet per. Time is measured here in seconds, so this should be feet per second. So 25 over 3 feet per second. That's the speed at which the shadow is moving. And keep in mind, because x didn't even factor into this, that's the speed of the shadow all the time. So the shadow's moving at a constant rate. The person's moving at a constant rate. The tip of his shadow is also moving at a constant rate relative to the pole. And that sometimes is counterintuitive. People don't think that that's the way it would work in a problem like this, but it does. All right, sorry about that arithmetic error. That just proves to you I don't work these out before I do them. It's always a little more exciting that way for me. All right, number 16. A spotlight